So lesson 4.1, forces in motion, part 2. So in this part, we're going to go over and continue on with the ideas relating them to Newton's laws. So first of all, what let's talk about an object when it's in equilibrium. What does it mean when an object is in equilibrium? When an object is in equilibrium, it could be in three different scenarios. So first of all, so scenario 1 is if the net force on an object is 0. What does it mean when the net force on the object is 0? So if I have like a box here and I apply force here 10 and force here 10 and the net force, and they cancel out, right? So same magnitude, different direction. So the net force here is 0. So that means what? The object is in equilibrium. So this is the first case, case 1 of equilibrium. Now, case 2 is, for example, when an object is moving and it doesn't stop moving, so it's at a constant velocity. So if I have a car here, or a truck or whatever, and this truck is moving at 20 meters per second, and it continues to move at 20 meters per second without changing its velocity, so it's at a constant velocity, that means it's also in equilibrium. So that's case 2. Now, the final case is if it's at rest. So if I have a book here and it's on a different color on this table and it's not moving, that means the velocity here is 0, but not only that, the acceleration here is also 0. So case 3 is if you say it's at rest. And that is case 3. So in these three cases, an object is in equilibrium. Now, why do I care if an object is in equilibrium? Well, you should know that there's something called inertia. And inertia is the resistance of an object in equilibrium, or the resistance in change. That is what inertia means. It's the resistance of an object to change. So for example, if I have this refrigerator that I want to move, like it's a refrigerator, and I want to move it like to a different side of my kitchen, the resistance of the inertia would want to resist me pushing it would want to resist me pushing this refrigerator in a different direction or a different place, because it's at rest right now, right? It's in equilibrium, it's not moving. And when I move it, when I change its position, I'm moving it, meaning that I'm gonna move this object from the equilibrium state to the moving state, or just in general, just moving. So there's gonna be the force of inertia, which is resisting my push. So if I have a smaller object, like a small box that's like 20 kg, and this refrigerator is 200 kg, for example, hypothetically, would the inertia of this refrigerator be the same inertia force of this box? And I'm going to tell you that no. The greater the mass of the object, the stronger the resistance to change it'll be. Like, for example, if I want to move a building or some like very big thing with a lot of mass, it's going to be a lot harder than moving a small box, So the higher the mass, the higher the inertia, and the lower the mass, the lower the inertia. So we stated before that inertia is the resistance to an object's motion, or basically to resist an object to change from the equilibrium state to the normal state. So we can also relate this to Newton's first law. First law. Now this law, it states here that an object at rest will remain at rest, meaning that if there's a box and it's sitting on a table, it'll stay on the table. And an object at motion continues in motion with constant velocity, unless acted upon by an unbalanced force. So this is also called the law of inertia. Why is it called the law of inertia? Because inertia states that it wants to keep an object at rest. So unless an unbalanced force is acting on this object, the law of inertia will take place, meaning that the law of inertia will keep this object and remain at rest unless there's a force that acts on this object. Like, for example, I push this object with my hand and it moves, then it is going to move. So the law of inertia keeps this object at rest, or the Newton's first law, and unless there's an unbalanced force acting on it, it'll continue to stay in the same place. So say I had two different scenarios. So I have this person, scenario 1, and I have this person, we'll draw a different color, it'll be my scenario 2. And in both scenarios, the person 1 and person 2, person 1 will kick the ball at a force of 20 newtons, and person 2 will also kick the ball at the force of 20 newtons. Now my question to you is, if this ball here is 5 kg and the ball here is 1 kg, which ball will travel further? Now immediately you're going to tell me it's the 1 kg ball, right? Because it's lighter. So the lighter the ball, the further it'll go, right? So my question is, why? Why does the ball go further? And the answer to this question is because it will resist less change, right? Didn't we say that the law of inertia means that the greater the mass, the more inertia it is, and the less the mass, the less amount of inertia it'll have. So because it has less amount of inertia, it'll resist the change of being at a state of rest. But there's a way you can relate this kind of scenario using a formula. This is called Newton's second law. And it states that the F net, we'll draw it in red, the F net is equal to the mass of an object, so m multiplied by its acceleration. So we can actually see Newton's second law at work here. For example, if I shoot the ball at 20 newtons, the mass of the object, which is at 1 kg, we can calculate the acceleration, which is going to be an acceleration of 20 meters per second squared. That's for the first ball. But if we calculate the acceleration of the second ball, which is the same exact method, so we have the mass and the F net, you can see that the ball is going to actually accelerate at a much less rate. So it's going to go a lot shorter of a distance. So if this is it's going to travel 4 meters per second in this amount of time, and here it's going to travel 20 meters per second, so a lot further. So our hypothesis in the beginning, saying that this ball will travel further, is actually true. And we even proved it using Newton's second law. So for Newton's second law, it states that the acceleration in an object, A, and note that this acceleration is in the direction of the net force. So the acceleration goes into the direction of the net force. You're not going to have an object whose net force is 20 newtons to the right, and it's going to accelerate to the left. That never happens. So the acceleration of the object is directly proportional, so it's going to be equal to, and proportional to the net force, so F net, and inversely proportional to its mass, so m. So we can relate this by saying that the F net is equal to the mass multiplied by the acceleration. And this formula is the basis for basically most force interactions. So we're going to see it in lesson 4.2, 4.3, and even in this lesson, so it's very important that you understand it. So let's start solving with examples to better understand how this lesson works. So this is from the first part of the lesson. We have to calculate the net force, and then we want to calculate the acceleration of the object. So calculate net force, and then calculate the acceleration of this object. So first of all, let's calculate its net force. So we want to do the horizontal axis, the vertical first. So let me pick a better color for this. Vertical, and then we want to do the horizontal as well. So for the vertical, it's going to be 12 plus 6 plus 3 minus 21. So this is actually going to be 0. So we don't even need to consider this because it's already in equilibrium. So f net of y equal to 0. Now for f net of x, we need to add forces here. So 10 to the right, 7 to the right, and 6 to the right. So we can say 10 plus 7 plus 6, and then minus 12 to the left and 9 to the left, minus 12, minus 9. And f net is going to be, x is going to be equal to 7 plus 6, 13 plus 2, 23, 11, 2. So it's important to note here that we're considering the left to be a negative and the right to be positive, which is why if you go to the left, it's negative, and if you go to the right, it's positive. Same with going up and down. So now that we know the f net of x, we know the f net of the total thing because f net of y is 0, so we don't even need to include it. So the whole total f net, but with a better color. So f net is equal to 2. Now, if you remember Newton's second law, you apply Newton's second law when an unbalanced force is being acted on an object. And here there is an unbalanced force, right? There's f net isn't 0. So we can apply f net. We can apply f net equal to ma, knowing because there's an unbalanced force. Now we have the f net, and we can calculate the acceleration using it. So f net is 2, so we can substitute. So it's 2. It's going to be equal to the mass, which is 5. So 5, and the acceleration unknown. Simply divide, and the acceleration is going to equal to about 0.4 meters per second squared. And that is our answer. A 5 kg block is pulled horizontally by a force of 20 newtons. So you have this block on a ground, and it's being pulled by a force of 20 newtons. So I guess draw the arrow going this way. Oh wait, it says to the right. On a rough horizontal table, the block travels at a constant velocity. What does constant velocity mean? It means that the acceleration, so a is equal to 0. Constant velocity. Calculate the force of friction acting on the block. So once the force acting against it, so there's going to be some kind of force resisting this block, which is 5 kg. So knowing that the object is acceleration 0, we can use Newton's second law, saying relating that f net is equal to ma. Now we know that f net has 2 different forces, so we can say that 20, so 20 is going to the right, so plus 20, minus this force that we do not know, so minus force x, is going to be equal to mass times acceleration. But acceleration here is 0, right? So this can cross out, and it's 0, so this is going to be equal to 0. Now knowing this, we can simply add x and add x, so the force acting against it is going to be equal to 20 newtons. So we can write here 20 newtons to the left. Why is it to the left? Because it's friction and it's acting against the object. So the answer to this question is 20 newtons to the left. So for this next question, we have two forces of magnitudes F1 and F2, 110 and 60 respectively, and they act on the same 8 kg object, kg box of pins. So we have this box, so this is our ground, and we have this box of pins, and it is 8 kgs, so 8 kg. And we have two different forces. Now it didn't tell us the direction, so we should note that. Now assume that these forces are the only unbalanced forces acting on this box. So these are the only forces acting on this block. There's nothing else acting on it. What is the magnitude of the greatest acceleration? Now you should know that when it says the greatest acceleration, it means that the highest amount or the greatest acceleration of an object. And when can an object accelerate more? If we look at F net is equal to ma. When does an object increase its acceleration? Either when you increase the force, so you increase the F net. Let's redraw it actually. So A is equal to F net over m, right? So when does the force increase? When we increase A, when we increase the F net, right? So F20 over, for example, 5. If we increase this to 40, this is going to be equal to 4. But if we increase this to 40 over 5, this is going to be equal to 8. So increasing the force increases the acceleration. What else increases the acceleration? If we decrease the mass. So if we have 20 over 10, it's going to be equal to 2. But if I have 20 over 2, it's going to be equal to 10. So this increased the acceleration by reducing the mass. So there's two ways. Either I increase the force or I reduce the mass, and these together will increase my acceleration. So if I want the greatest acceleration, I have two forces, and if I increase the forces, I can increase acceleration. So if I add these, then it's going to give us the greatest F net. But if I subtract them, it'll give me a smaller F net. So to get the greatest acceleration, I should add the two forces. So then both forces are acting in the same direction. So I have 110 here, and I have 60 here. And we can simply use F net is equal to ma. And if we add these, it's going to be 170. Is equal to the mass, which is 8, then A. If I do this on a calculator, A is going to be equal to 21.25 meters per second squared. So the graph below shows the acceleration versus the net force. So acceleration v net force, so F net, of a moving object, and wants to know the mass. So what do we know about acceleration, net force, and mass? We know that the relation F net is equal to ma. We know this relationship. So if we want to calculate the mass, we divide by A, and then we get the mass is equal to the F net over the acceleration. So what can we do here? Simply take any point. We can take any point we want. We can take the easiest point here, 4, and we just plot it inside this formula, right? So F net is 1. So we're going to do 1 over, and then acceleration, it's 4. So 1 over 4. And then we just plot it in the graph, in the formula like that, and then you get your answer, 0.25 kg, or whatever unit it gives you in multiple choice. So for this next question, we have a skydiver of a mass 50 kg, and he is mid-jump. So he just jumped off his plane or jet. And he has an instantaneous acceleration of 4 meters per second downwards. So what is the gravitational force exerted by the Earth on the diver? So it wants to know the gravitational force. So first of all, look, whenever you have these types of questions, we should draw the free body diagram. So we have this person, he just jumped off the plane, and he has an instantaneous acceleration of 4 meters per second, and his mass is 50 kgs. So first of all, we should know that the only force acting on this object, or this person, is the force of gravity, so mg, And to calculate the force of gravity, you do mass times gravity. So mass is 50 times 10, right? It gave us force of gravity. So the force of gravity is going to be equal to 500 newtons. So for the second part of the question, so this is part B, this is part A. Second part, it asks, it wants to know the resistive force exerted on the air by the air on the diver. So the diver, again, we'll redraw him. So we have the gravity downwards, G, and we have some kind of resistive force of unknown value upwards, and we want to calculate it. So first of all, whenever we have multiple forces, we don't know the F net, so we should write these forces in F net. So the F net here is equal to what? It's equal to the force downwards, which is 500, so it's negative. So we can write, so X is this force, minus 500. And this is our F net. Now we can pop this F net into our formula, which is F net is equal to MA. So we have X minus 500 is equal to the mass multiplied by the acceleration, which is mass is 4, acceleration, mass is 50, sorry, acceleration is 4. So X is equal to, X minus 500 is equal to 200, plus 500, sorry, the acceleration here is minus 4. Why is it minus 4? Because it says 4 meters per second downwards. And if you remember correctly, when we're considering acceleration, you should know that when it's downwards, it's negative, and when it's upwards, it's positive. So since acceleration is downwards, it's going to be minus 4 meters per second squared. So because of that, it's minus 200. So when we add plus 500, it's 500. X is going to be equal to 300 newtons. And now 300 newtons where? Since it's a drag force and it's going to resist this, it's going to be 300 newtons upwards. That is our answer. A constant force of 30 newtons acts on a 10 kg box, as shown in this diagram. So if the box is originally at rest, this means that the V initial is 0. What will be its velocity after 5 seconds? So it wants to know the V final after what? 5 seconds. 5 seconds. So first of all, we need to calculate the acceleration. But first of all, let's find the formula needed to find the V final. So we have one of 4 formulas we can use, and we want to relate the acceleration. So A with V initial and V final and time. So this is the formula we will use. So we need the acceleration, which isn't given here, so we can calculate it using the F net here. So here, to calculate the acceleration, we do F net equal to mass times acceleration. F net is minus 30 newtons, right? Because it's going to the left. It's equal to the mass, which is 10, acceleration, which is unknown. Dividing this by 10, we get the acceleration is going to be equal to minus 3 meters per second squared. So now that we know the acceleration, we can calculate the V final, which is going to be equal to the V initial, so 0. So we're basically plotting this formula. Draw in a different color. So the V final equal to the V initial, 0, plus the acceleration, which is minus 3 meters per second. So minus 3 multiplied by the time, which is 5, and the V final is going to be equal to negative 15 meters per second. That is our answer. That'll be it for lesson 4.1, force and motion. If you have any questions or want to ask anything at all, you can ask it down below in the comment section or in the Discord. And yeah, good luck.